Section 4.5, integration by substitution. As we're looking at, just gotten done with the fundamental theorem connecting antiderivatives to these definite integrals to make that a little easier to doing, but we still have just the basics we can work with. Now we want to start looking at more complicated functions. We're going to look at a few things. We're going to use pattern recognition to see, can I recognize again one of these intervals? Kind of like what we're doing with our table, our values that we found in section 1 of antiderivatives, but taking this next step beyond. We're going to use change of variables to help us find these integrals and get to a general power rule for integration. Then we'll look at applying this to definite integrals, and finally finish up with even and odd functions. As we've been looking at these, we've been kind of stumped. We're stuck with the fact we don't have a product rule or a quotient rule. We don't have a chain rule for integration. So how do we deal with these more complicated functions? So again, our two methods we're going to talk about in this lesson are pattern recognition, and change of variables. Really, they're the same things, but we're going to look at pattern recognition is basically where we can recognize, hey, I know what this looks like. I can do that change of variables mentally without having to formally do that. But we're going to start with that because that kind of eases us in here a little bit more. The idea is we're trying to deal with something similar to the chain rule. So if you start with the chain rule and work backwards, because we know derivatives and integrals are two sides of the same coin, they're inverses of each other. So we know that if I have the derivative of f of g of x, that's the derivative of f evaluated at g times the derivative of g. So what we're going to do is use that backwards and say, well, if the derivative of this is that means the integral of this, f prime of g of x times g prime, is going to be our f of g of x. That's that idea, that pattern we're going to start looking for. And this is just the theorem to say it, spell it out. We're looking at if I'm doing the integral of f of g of x times g prime of x, that's the antiderivative of f evaluated at g of x plus c. And this kind of disappears out because, again, coming back from the chain rule, that gets thrown in the derivative of the process, so it kind of gets absorbed back in when we go backwards. So this is your idea, that u-substitution that I kind of mentioned and we'll do more with. But we're saying if u is g of x, du is g prime dx. So that makes this f of u times du. This is that one pattern. If we can see this, we can make our work easier. So using this pattern, recognizing it, I look at this one here, and here is my composite function. I have something raised to the second power. So my f would be x squared, and my g is x squared plus 1. And then we're squaring that. Well, so if my g of x is x squared plus 1, the derivative of x squared plus 1 is 2x. So we see here we have the composite function and the derivative in here. So we say my function f was just x squared, f of g of x. So this is how it all fits together. So the antiderivative of x squared is 1/3 x cubed. We're evaluating that at g of x, so it's 1/3 x squared plus 1 to the third power. And so our integral, we have that f of g of x times g prime of x pattern. is just the antiderivative of f evaluated at g. With a little practice, you start doing this a lot easier. We'll go through... Did I go too far? No, I didn't. We'll go through it with this example. Give it a try if you think you're making sense of that. Pause the video and come back when you got it and want to check, or if it's not making sense and you want to see an example. See another one going through with this. So this is going to be my f of g of x, is my sign to the fourth. So we're taking something to the fourth power. My f of x is going to be x to the fourth, so my g of x is just the sine of x. So the cosine, g prime of x, the derivative of sine is the cosine of x. So we put this together, and here's my f of g of x times my g prime of x. So I can rewrite this as the integral of u to the fourth du, which is going to be 1/5 u to the fifth plus a constant. And my u, which is my g of x, is just sine x. So this is 1/5 sine to the fifth x plus your constant. As I say, if you recognize that pattern, this is a quick and easy way to do it. If you don't recognize the pattern, we're going to go on to our other methods. But we're just going to start. This is a pattern that is really nice if you see it. So we want to play a little bit with that and practice with that some. Now, let's look at this one. If we look at this whole idea, we have my g of x would be x squared plus 1, and I'm squaring it. My g prime of x is 2x. I don't have 2x in here, I just have x. So in order to use this pattern, I need 2x there instead of x. So I can multiply in a 2 if I multiply in a half as well, because 1/2 times 2 is 1. I haven't changed it, but now I have this 2 in here, and I can use the constant multiple rule to pull that 1/2 out. So I can take half of the integral of x squared plus 1 squared times 2x dx. And now I have f of g of x, and I have g prime of x. So I can just apply my pattern and take, okay, that would be my 1/2 from the constant multiple. I have my u cubed over 3, or my x squared plus 1 cubed over 3, plus my constant. So we might sometimes have to play some games. If it's just a constant, we have a constant multiple to deal with that. Now, if you don't recognize it, that's fine. We'll do it a little bit more formally. I'm doing this using this u in there, this u-substitution. It's generally back here. What we're doing is we're changing our variables. We're going to use this Leibniz notation for the differentials we got from last chapter, the end of chapter 3. And if we say, okay, I think I have a composite function here going on. I let u is g of x, then du is g prime of x dx. And then that makes f of g of x becomes f of u, and g prime of x dx becomes du. And so I have the integral of f of u du, which is just f of u plus c. So, for example here, we're going to get u be 2x minus 1, because that's what's inside the function here. Then du is 2 dx, and I'm just going to solve that for dx. So I divide by 2 and say dx is du. Now I can substitute these in. I can substitute u for 2x minus 1 and du over 2 for dx. So I get the square root of u times du over 2. That's our change of variables. Now I'm going to use the constant multiple rule, take the 1/2 out, change this to an exponent because that makes it easier. I can use my power rule. So I get 1/2 u to the 3/2 over 3/2, or 1/3 u to the 3/2 plus c. So change of variables. This deals with that, oh, do I have to then multiply, then divide to make that constant work? When we do it this way, it just kind of, we work it into it as we do it. Finally, what we have to do is, well, we have this in terms of u. I want it in terms of x. Well, u is 2x minus 1. So I just plug in 2x minus 1 for u. So let's go ahead and try this one. Here's a problem. When I put this x up here, I can then go 2x minus 1, okay? Dx is du over 2, that same thing. But now I have x in here. I can't have another variable. I'm switching this over to the integral we're doing in terms of u. I can't have x because x is another variable. So this is a trick we sometimes do. Sometimes this works, sometimes it doesn't. But if I can say, well, if u is 2x minus 1, x is u plus 1 over 2, I can substitute that in place of the x. So I got u plus 1 over 2 times u to the half times du over 2. Now I can pull out my constants here, so take out the 1/4, and I can then take u to the 1/2 times u plus 1 is u to the 3/2 plus u to the 1/2. Now that's something I can do. I can break that apart into the sum of the integrals. I can use my power rule. And I can clean up that because I never want to leave a fraction inside a fraction. So I change those to multiply by the reciprocal, take them times 1/4, simplify that out, and there we go. So this is something that I couldn't recognize with the pattern because of that extra x in there. But as we're doing this change of variables, sometimes we might have to replace an x in the function with a u to see what that does and see if that can help us out. So, general guidelines. Choose your substitution. Generally look for a composite function, especially these are used a lot for quantities raised to a power. Find du, g prime dx, and then you're going to rewrite the integral in terms of u. You're going to have to do some substitution here, some rewriting. But now, hopefully, that integral in terms of u is something you can integrate, and then once you've done that, you then back substitute the u back to in terms of x to get in terms of x, and always check your answers by taking the derivative and see if it works out. So that gives us the general power rule for integration. General power rule for integration is pretty much the pattern we looked at, but we just kind of spell this out. If we're looking at a function to a power times the derivative of the function, that integral is just that function to the n plus 1 power over n plus 1, add the constant to it. So you could look at that pattern recognition. We get this down to the u-substitution. That's the integral of u to the n du. So look for options to be able to use this. This might be easier to do with just working some examples. So see what you can do with these. Work these out, then come back. Or let me work through one for you, and then pause it and see what you can do with the rest of them, and come back and forth. Let's see. Try to work these through yourself as much as you can. So on here, my g of x is 3x squared minus 7. So our g prime of x is going to be 6x. So we can say this would be the integral of u to the 4th du, because my dx is going to be 6x du. So that's going to be u to the 5th over 5 plus c. So we're going to get 3x squared minus 7 to the 5th power over 5 plus c. On here I have two parentheses, but here's my power, so I'm going to make this my g of x. So my derivative of that is going to be 4 times 3 is 12x cubed minus 5, which is right here. So here's my f of g of x, and here's my g prime of x. So I'm looking at the integral of u to the 3rd du is going to be u to the 4th over 4 plus c. And that's going to be, I'll write this one, 1/4 times 3x to the 4th minus 5x. And all of that is to the 4th power. Plus our constant. Don't forget our constant. C. I'm going to look at, say, here's my function. So this is x squared plus 7x plus 5. Minus 5, sorry. So my derivative is going to be 2x plus 7, which, hey, we got that convenient here. So again, we can say this is just the integral of u to the negative 1/2 du. And that's going to be u to the 1/2 over 1/2 plus c. So that's going to be 2 times the square root of x squared plus 7x minus 5. Don't forget your c. If you can recognize this pattern, it goes pretty slick and easy. If you don't, well, then we just work through it one of the other ways. Generally, you work through with substitution. Now here we have secant squared and tangent squared. So you have two different functions that are being squared. So you have to start thinking, well, the derivative of, or which one of these is going to be the derivative of the other. The derivative of the secant Yeah, the derivative of tangent is secant squared. So since I know that one, I gotta say which one looks easier to do. Which one we want to say, do I see the derivative? If I make g of x equal the tangent of x, then I can say g prime of x, the derivative of tangent, is secant squared x. So I have that based into here. But you have to know your derivatives enough to be able to recognize that in there. So we're looking at the derivative, or the integral, of u squared du is going to be 1/3 u to the third plus c. So that is going to be 1/3 times the tangent cubed of x plus c. This is kind of a good place to stop. So in the second part of this video, this lesson, I will start looking at, we've been working with indefinite integrals. I'll start looking at definite integrals and how we do this substitution with the definite integrals.